Hello everyone, today we're going to present to you industrial production of recombinant chymosin. We are Sebastián Zurita, Valeria de la Vega, and Austin Nicolalde. Today we're going to look a little of introduction, why it's important, this investigation, how the chymosin works with the milk to produce cheese. We're going to look at a flow diagram for looking the biotechnological way to produce chymosin, and we're going to look a little of costs and the efficiency of products similar to the one we present today. So a little of introduction, why this is important. First of all, we have to look at a common product that people use in the cheese industry, and it's the rennet, a natural rennet. Rennet is obtained from calf stomach and has been used as a coagulant in cheese industry. A coagulant is a chemical that can solidify the medium, and in this case solidify the milk for making the cheese. So the natural rennet has been the way for making cheese, but nowadays there are better ways to do it, and there are reasons for it. Two main reasons for making biotechnological chymosin is the decrease in the slaughter of calves of the animals that we want for obtain the rennet. This is the case because nowadays people want products that don't kill animals necessarily. So that way the industry reduces the kills of animals, and also the cheese production is increasing because the demand of cheese is also increasing. So the industry needs chymosin that can be made in a large, big production, and that can make a lot of cheese. That means that it has to have a lot of efficiency. So there are many ways to make chymosin depending on the origin of the biological material. It could be from microbial origin, from animal origin, or from vegetable origin. In this case, we're going to talk about a microbial origin, specifically E. coli bacteria. So it's important to note that the chymosin is a protease. A protease is an enzyme that breaks down proteins, and we're going to look at breaking down a specific protein. We can make the chymosin act on milk for making cheese. It's also important to note that this new discovery only has like 1 or 2 decades. So it's already a massive production from some industry making products by only biotechnological ways of chymosin. Some examples are Chymax, Chymogen, and Maxiren. Now we're going to talk about chymosin and industrial cheese production. So as we said, chymosin coagulates the milk. For making this, we have to take care of the pH of the medium. The pH of the medium has to be low, it has to be more acid. That is to say, in values between 3 and 5 pH. So as I said before, the chymosin is a protease. So the protein that the chymosin breaks specifically is the K casein. And this breaking of K casein produces an effect, and this effect is called clotting. This name is a fancy way to say the solidifying of the milk. After the clotting we have the curd, and curd is the first step for the cheese production when we already have solidified milk. Now, we're going to talk about chymosin and mechanism of action. So, the specific material for making cheese obviously is milk. Milk is composed of water, of fats, of proteins, of minerals, of vitamins, and calcium phosphate, lactose. But in this composition, the most important things are proteins. the proteins are what we're looking for in the chymosin action. The proteins in the milk is divided into groups: casein fraction and whey proteins. In whey proteins we have subgroups. We have lactoglobulins and immunoglobulins and serum albumins, and they can be beta and alpha. But the most important fraction of these proteins are the casein fraction. In this we have alpha casein, beta casein, and the K casein, the one we have already talked about. So the K casein is the most important here in the process. And I'm going to explain to you how this works. Here we have a casein micelle. In this casein micelle we have the three types of casein I already mentioned inside of the micelle. An important feature of this micelle is that it has negative charges around the whole micelle. This negative charge is the thing that do not allow another casein micelles to join. And if they don't join, they cannot create this complex coagulation formation. And if this doesn't happen, we cannot have a cord. So the first step is to break down or take down the negative charges. Normally, people in past years use a lemon, for example, to taking down the negative charges by putting hydrogen, H plus molecules. So if they take down the negative charges, they can have now the possibility to attack the K casein. But if people use lemon, for example, they can change the taste of the product. So a better way to do it is using chymosin, because this enzyme can take down the negative charges and also attack the K casein, allowing for making the micelle coagulates. So now we're going to look how this is done. Look specifically how the chymosin mechanism of action works. So we have here the K casein. This K casein is divided in two fractions, the hydrophobic and the isophilic. Also, it's made up of 4 amino acids: the his, the phenylalanine, the methionine, and lys. The chymosin is very specific in the space where it cuts. Chymosin cuts between the phenylalanine and methionine bond, between the 105 and 106. When chymosin takes down all the negative charges and attack the K casein is divided in two, in para-K casein and in glucomacropeptide. The hydrophilic part go away from the micelle, and that way the micelle that has been opened, for a way to say, can join another one, and this complex to another one, and all the conglomerations of open micelles creates the cord that we want. And we have to remember that this cord is only possible if we have a pH below 5 or 5. Now we're going to look at industrial production.
This is the flow diagram of the industrial production of chymosin. The first step that we need to take in account is to take a piece of the tissue of the calf's stomach and isolate the DNA from the other cells. In this step, it is important to use the DNase blood and tissue kit, which provide the purification and isolation of the total DNA of animal blood and tissue, and from cells, yeast, bacteria, viruses, and other microorganisms. After the isolation, it is important to amplify the chymosin gene with PCR. In the PCR, it is performed using a degenerate sense primer, the first one, and the antisense primer. The amplifications need to have to has 850 base pairs of the chymosin gene. After the amplification, it is important to introduce the gene into the plasmid and the plasmid into the microbe, that in this case we are using E. coli, K12 strain in PBR322 plasmid. In this clonation, is done using a TA-based cloning protocol using a PCR 2.1 TOPO cloning vector and a TOP10 E. coli strain. The chymosin is released using a PCR 2.1 TOPO vector and using an ECOR strain 1 restriction enzyme. The released fragment was purified using this extraction kit and was ligated to a linearized prokaryotic expression. Once the clonation is done, it is important to inoculate the bacteria in an LB medium. This is a common medium used to the maintaining and development of the recombinant DNA of E. coli. Then it is important to choose the bacteria that is resistant to antibiotics and introduce it into the seed fermenter. The seed fermenter needs to have some conditions, like it has 2 grams of potassium phosphate monobasic, 3 grams per liter of potassium phosphate, 5 grams per liter of ammonium phosphate dibasic, 5 grams of yeast extract, and 0.5 through 0.4 of antifoam to inhibit bubbles. Also, I need to have a 25 Celsius degrees of temperature, a pH of 5, and 250 RPM. It is important to mention that the E. coli K12 strain has the prochymosin gene under the control of the TRP promoter PBR322 vector system. Then the inoculum is transferred to the main fermenter that needs to have some conditions, like 25 grams of glucose, 0.5 grams per liter of magnesium sulfate, 1 milligram of thiamine, and 5 milliliters of K12 trace metal solution.
Then we need to transfer it to a seed fermenter. The bacteria is transported to the main fermenter, which helps bacteria to grow. Because the machine maintains the microorganisms in a controlled environment, we need to adjust some parameters like temperature at 37 degrees Celsius, 7 of pH, and we need a taste of dissolved oxygen of 35%, and agitation at 300 to 100 to 1200 revolutions per minute. This device works continuously because it adds a substrate periodically to allow the bacteria to grow constantly. Well, after the main fermenter, we need to transfer it to the homogenizer. We put it in the homogenizer that disrupts the cells and produces the lysis in these machines. It's important to the result that is a single stage homogenizer. After the lysis, we need to input the machine at a pressure of 600 to 1000 bar. The shells should therefore be cooled at 4 degrees Celsius prior to use to avoid inactivating proteins by fuming. After the homogenization, we need to put it in a centrifuge to the centrifugation. For this, once the lysis is formed, it is centrifugated to separate the lysis in different phases. This process consists in 5,000 revolutions per minute for 15 minutes at a temperature of 4 degrees Celsius. Okay, then the centrifugation, we need to do the harvest or refolding. In this step, the different phases are transferred to a harvest step where the DNA breaks into pieces. In this step, the harvest inclusion bodies are washed with phosphate buffer solutions containing 1 to 4 moles of urea. The residual E. coli are inactivated with a pH lower than 2 for at least 1 hour. Then we need to dissolve this by addition of urea between 7 to 9 moles and a pH of 10 to 11. The solution with Chymosin is diluted with a buffer, and the pH is reduced to 1.5 to 9.5. 2 hours period to allow renaturing of the Chymosin, which is activated to chymosin by a pH of 1.8 to 2.2 for 1 hour. Okay, following by a 2 hours period to allowing renaturing of the proto-chymosins, which is subsequently activated. The chymosin by adjusted the pH to 1.8 to 2.2 and holding for another hour. Finally, we need to readjust the pH to 5.5 to 6.0 because the chymosin is purified by absorption on a suitable anion exchange resin, following by elution with a buffer containing 1 millimole of sodium chloride. Then is doing the filtration to make easier the purification by chromatography than we see it here. Yeah, for the purification, we need to crude the crude enzyme solution is produced. To purify and concentrate the enzyme, we need to use an anion exchange chromatography where the column was equilibrated with 19% of 0.05 moles of formaldehyde acid and 1% of sodium chloride, in addition of 10% of acetonitrile. Following by a 20 minutes of gradient to 40% of acid formate and 60% of acetonitrile. The flow rate was 0.1 milliliters per minute, and elution was monitored at 280 nanometers.
Okay, so now it's important to take care about the cost of all this procedure, all about the diagram we propose. So for almost every step, there was a machine for making the process, for making, for example, the chromatography, the homogenizer, the centrifuge, the fermenters. So we have the equipment that we found, and we right here have the prices. All the prices are for a low production. Specifically, in this stainless steel jacket stark tank reactor for a production of 10,000 liters. So we have all these prices. If we sum them up, we have $16,500. But that will be only a cost for all the machinery. It is also important to take care of other costs like the employees for this procedure, considering that we have to train them a lot, the implements for the laboratory and things like that. So we consider that initial price for making all this possible could be $20,000 production for initial production. So it's also notable to ask ourselves if it is viable, if we can produce a final product that is attractive for our customers. So we can have a very interesting comparison between a Marshall chymosin that is from Ecuador and a chymosin recombinant renin that is from USA. This one, the chymosin recombinant renin USA, is using the same steps that we propose here. This one is using a fermentation process, but it's not using the same one that we're using here. And this one, the chymosin recombinant renin process, is known for making almost 100% of purification of the chymosin. But in this case, as we research, we found that in the ingredients were another things like water and another salts. Here are a more purified chymosin. So, well, let's look at the prices. For example, in the Marshall one, 1 liter costs $25. In the chymosin recombinant renin, we have per 10 milliliters, it has a cost of $28. But if we want to make this for 1 liter, we have $280. So in a first impression, a customer may want this one, the $25 per liter. But it's also important to note the efficiency of this product. That is to say, how much of the product I need for making a certain amount of cheese, a certain amount of curd specifically. We found that in this one, in Marshall product, we need 5 milliliters to make a curd of 75 liters of curd. But in this one, the chymosin recombinant renin, it's more efficient, the process. We only need 1 milliliter of the chymosin to make 100 liters of curd. So we can see an important difference here. And if we take the efficiency of making a lot more of curd, we can choose the chymosin recombinant renin process. And it's only the only issue is to tell the customer that a liter of this chymosin will cost a lot, but it will last a lot of time and it will produce a lot of more curd. So in the end, let's remember, the right one produces 100 liters of curd by only using 1 milliliter, and the left one uses 5 milliliters to produce 5 liters. It was not 75 liters. So it's a lot of difference. So in the end, it's only a cost of the machinery. If the company that want to take this approach, they will have to have the 20,000 minimum to take advantage of the chymosin recombinant renin product. So we think that it is possible here in Ecuador, and it's a viable option because it's not so common nowadays. So that's what we it. Thank you for your attention.